Math 265A, Calculus 1, Cuesta College. I'm Joe Vasta, and this is section 4.2, the mean value theorem. Now, in the previous lecture we covered bug 10, which was really the mean value theorem, so this is just going to kind of be a repeat. There's going to be a few other things in here, and there's our mean value theorem that says you have a function that's continuous on a closed interval AB, and it's differentiable on that open interval AB. Then there's a c in that interval, so c is like an x value, such that f prime of c equals f of b minus f of a over b minus a. And the way that we can think of it is that if this is the position of the bug on the number line, then there's a time within the time interval where the instantaneous velocity equals the average velocity of the time interval. So that's the way I like seeing the mean value theorem. So let's go ahead and prepare ourselves for some of the homework in 4.2. So the first one here, they'll ask you determine whether the mean value theorem applies, and then if so, find the points that are guaranteed to exist by the mean value theorem. Now, on the last lecture, that's exactly what we did. We found the time that existed within the time interval. So first of all, does the mean value theorem apply? So here we go. The mean value theorem says f is continuous on 0 to 5. Is f continuous there? No. F is not continuous. And then in particular at time 1. At 1. So look, 1 blows up that function. So if the hypothesis of the theorem is not satisfied, then the mean value theorem does not apply. So our answer to this problem is does not apply. And when we say does not apply, we mean the mean value theorem does not apply. So I think maybe we should go ahead and do another problem. So here's a problem. It says f of x equals the square root of x, and we're given a time interval from 1 to 4. So part A says for us to determine whether the mean value theorem applies, is f continuous from 1 to 4? And the answer is yes. This is the square root graph. You know, if you're thinking about what the graph looks like, it's a half a parabola. It's nice and smooth and continuous from 0 or to the right of 0 all the way to infinity. So it's continuous on that time interval or that x interval. And it's also differentiable. It's nice and smooth, no corners or cusps or sharp points. So we're good to go. So part A on this, you know, for the answer, and I know, you know, on this one I should have said part A does not apply, part B not applicable. Okay? So on this one, part A, the mean value theorem does apply. So we'll say applies, whatever that means. You know. Yeah. Almost looks like apples. Huh. Okay, part B. So what did part B ask us to do? It says, if so, find the points that are guaranteed to exist by the mean value theorem. So what we want to do is the mean value theorem. Okay, so let's go. So we're trying to find the points that exist. We have to compute two things. The first thing we want to do is compute, let's just call it the average velocity. Okay, so I'm going to compute the average velocity of this function. So this is f of 4 minus f of 1 all over 4 minus 1. Okay, f of 4 happens to be, you put that in there, and I picked nice numbers for this one. The square root of 4 is 2. f of 1 is 1. 4 minus 1. So this is going to give me 1/3. Okay, so we've just computed. Okay, let's kind of color code this. We've just computed that. Okay, what I want to do is take the derivative of the function and find a point within this time interval that will have a slope of that, or try to find a time that has instantaneous velocity 1/3. So my next step that I have to do is take the derivative. Before I take the derivative, let's go ahead and write this as x to the 1/2. So we're going to do the power rule of derivatives, 1/2 x to the negative 1/2, which is 1/2 root x. Okay, so what we want to do with this is we want to find a time in which when you put it in here it gives you 1/3. So let's try this out. What we're going to do is we're going to set the instantaneous velocity, that's f prime of x, which is this, equal to 1/3. And we did something similar with bug 10, and we're going to solve for x. So I'm going to cross multiply. I'm going to divide by 2. And so let me rearrange this equation so it says root x equals 3/2. Then what I'm going to do is I'm going to square both sides. So I end up getting x equals 9/4. There's the answer. So the mean value theorem applies, and then look, we only had one answer, but that answer, which is really, I mean, if you like, you can write this as 2 1/4. It does fall within that time interval. And so basically, we have found our answer. Now, what does this mean graphically? Let's go ahead and take a look at the graph on this. We have this right here. Our function square root of x is this orange guy right here. Okay, then I have these 2 points from 1 to 4, right there, to 4. I drew the secant line, which is in red, and that secant line has a slope of 1/3. Now once again, my scaling, just like in bug 10, is a little off. You know, I mean, it might not look exactly like 1/3 because the scaling on the y-axis looks different. But anyway, the secant line has slope 1/3. Well, now what the mean value theorem says is there is a point on this graph between those 2 points where the tangent line is going to have the same slope. And that point happened to be here, which we said was 2 1/4 or 9/4. So we actually found the time that gives us the instantaneous velocity of 1/3, the same as the average velocity. Now in your homework, they may have a few problems where they give you the graph and tell you to look at the graph and try to guess something from the graph. The important thing to do in your homework is what we just found here. Find the x value, or the time that is in that interval that has the same, that has the instantaneous velocity equaling this average velocity. Let's go ahead and do the next problem. But before we do the next problem, you may have noticed on this I had something covered up. So I'm going to go ahead and show you another theorem. It's called Rolle's theorem. So Rolle, my guess, was a person. He probably got made fun of, maybe in school. Maybe people call him Roly, Poly, or whatever. So he got mad and studied math and came up with this theorem. But you'll see this theorem is pretty cheap, because really all it's doing is we have f is continuous on a to b, closed interval. F is differentiable on a to b, so it looks like this. And then they say, look, f of a equals f of b. Basically, Rolle's theorem is just a special case of the mean value theorem, because it just throws this extra condition in. Well, notice if f of a equals f of b, what's going to happen here? Well, that's going to be 0 over some number. So it just says there is a c in the open interval such that f prime of c is 0. So this is sort of a rip-off of the mean value theorem. But it's called Rolle's theorem. So let's do a problem that has Rolle's theorem in it. And then we'll actually see an application in the real world of this. Okay, so let's go ahead and do problem number 3. Problem number 3, so it's kind of stated like problems 1 and 2, determine whether, mean value theorem applies, but now it says determine whether Rolle's theorem applies. If so, find the points that are guaranteed to exist by Rolle's theorem. Okay, so because this function is continuous and differentiable in this interval, then Rolle's theorem does apply. So, for part A, the answer is this, it applies. Okay. Part B says, if so, find the points that are guaranteed to exist by Rolle's theorem. So there's a point in here where this, well, actually, before I do this, I kind of jumped the gun. It's continuous and differentiable. One thing I should have checked, actually, before I did this, I should have checked if f of 1 equals f of 6. So I was bad. I did not check this, and this is one way. I'm still seeing if it does apply. So I have, if I put 1 in there, I have 1 squared minus 7 plus 9. So it looks like I have 3. And if I put 6 in there, I have 36 minus 42. 36 minus 42 is going to give me some negative 6, and then I have plus 9, which is 3. So yeah, now we can say that it applies, because we're doing Rolle's theorem here. Okay, so f of 1 equals f of 6. So if you're going to find the average velocity from 1 to 6, I mean, the average velocity would be 0. 0 feet per second. Now, of course, this wasn't phrased as a position function, but I'm just saying that's what the average velocity is. So what we want to do is we're doing part B, find the point or points that are guaranteed to exist. We want to take the derivative of this function, 2x minus 7. And we want to set the derivative equal to the average velocity, which with Rolle's theorem, it will always be 0. So let's go ahead and solve the equation that I have written there. This equation right here. So this is actually finding the critical point of this function. 2x equals 7, x equals 7/2. And so that is our answer. We have 2 answers. Part A, it applies. Rolle's theorem does. And part B is x equals 7/2, which is really 3.5. That helps you out there. We're done with the problem, but what we're going to do now is we're going to take a look at the picture. This graph is a graph of a parabola. So I'm going to put that graph of the parabola up, which looks like that. Okay, now f of 1 equals 3, and f of 6 equals 3. So if you graph the secant line, it has a slope of 0. So what they asked us to do in the problem is find a time between 1 and 6 where you'll have a tangent line equaling 0, and the tangent line equals 0 right here at this point, which looks like what on the x-axis. I know those numbers are really small, 3.5. And so that's what we found. Look at that. So there's the instantaneous velocity at 3.5 equals the average velocity of the time interval 1 to 6, which was the given time interval. And so that completes problem number 3. That should help you out with your homework. And so what I'm going to do now is this one right here. Cop 1 clocks famous orange car going 30 miles per hour. Okay, so let's say that cop 1 is right here. Okay, and the famous orange car is going 30 miles per hour. And it's like, it's going pretty fast. Okay. I guess we didn't need the sound effects, but I'm not going back and editing that out. So you get what you get. He radios Cop 2, who is 32 miles down the road. 32 miles away is Cop 2. And perhaps he's like saying, this is Roscoe P. Coltrane. Or, I mean, if you don't get the reference, then you're missing out on life. Okay, so 32 miles down the road, Roscoe is contacting Enos Strait. Man, where do they get those names? And he's saying the orange car is coming your way. Famous orange car passes Cop 2 20 minutes later. Cop 2 clocks famous orange car going 25 miles per hour. Okay? Speed limit is 65 miles per hour. So at first glance you're like, well, he doesn't seem, the famous orange car seems to be going a lot slower than the speed limit. But now that we have calculus, and maybe we could have done this without calculus, we can answer this question: was the famous orange car speeding? So, wow, what are we going to say about this? I'd like to know the average velocity. That's what I want to know. And the average velocity, before I do anything else, because I have miles per hour, I have 20 minutes, so I'm going to change that to hours. 20 minutes, what does that happen to be? That happens to be 1/3 hour, 1/3 of an hour. So instead of putting 20 minutes, famous orange pen here, we're going to put 1/3 hour. Now let's go ahead and do this. Remember, the average velocity is, we have the times on the bottom. Remember, we can say 1/3 minus 0, because we'll just start the clock at 0. And then the position is how far they went. I mean, you can say s of 1/3 minus s of 0, but really that is going to be how much the displacement was, or the position, which we see is just 32. So I could just put a 32 there. In fact, I could have just gone 32 divided by 1/3. And so I do a copy dot flip. 32 times 3 is 96. Let me say 96 miles per hour. And that is the average velocity. So here's the deal. By the mean value theorem, and let's see here, we by the mean value theorem, I've got to be careful not to write MTV, and I was thinking that I read it somewhere, but maybe I'll go back and check. The mean value theorem says there is a time where the instantaneous velocity equals the average velocity within that time interval, the time interval being 0 to 1/3. So I'll write that down. The mean value theorem says Okay, so I'll put a little arrow. There is a time where the instantaneous velocity equals the average velocity, which means the instantaneous velocity was 96 miles per hour. Okay, so that's what the mean value theorem says. It just happened to be that way because when you have this, we do have smooth continuous curves. We can assume that. When I say smooth, I mean differentiable and continuous. So the answer is, was the famous orange car speeding sometime along the line? The answer is yes. Okay. Now, they weren't speeding when they passed cop 1. Maybe they saw cop 1 and slowed down, and then when they got to cop 2, they were going even slower than when they passed cop 1. But sometime in between, they were going at one point, at least one point, 96 miles per hour. So, I mean, I guess there's a follow-up question. Who was driving? You're like, what? How could math answer that? I'll make it multiple choice. Bo, Luke. So, I mean, if you can answer this with 100% confidence, then you've got some 1970s culture in you. But in any case, we're going to end this lecture of 4.2, the mean value theorem. You guys have a good day, and I will see you on the next section.